Hello. Today's lesson we're going to be learning about how scientists learn about the universe, and it's the topic of the whole unit, but we're learning it more in general today. And specifically, and also primarily in class, you're going to be learning how to formulate hypotheses and how to simulate experiments in a card game. We're not going over the card game in the vodcast. This vodcast, like the others, it's just to give you the information that you need to put into your notes, and we're going to do the actual activities in class. Okay, the scientific method is what we call the method of how scientists learn about the universe. And ideally, this is done through experiments. And we'll be doing quite a few experiments throughout the year today in doing labs, and you're also going to be designing experiments too. Sometimes it's not possible to do experiments, and then you use observation rather than actually manipulating and changing things or doing something in a lab. And on here I have two examples of when it's not possible. Like a star's life cycle, that's not something that a scientist can do an experiment on. Several reasons. One is we only have one star that we could reach, and that star is responsible for life. Change things on that star, and you may end up destroying all life. And another reason is a star's life cycle is profoundly longer than any scientist can live. Our sun has been around for 4.5 billion years and be around for 5 billion years longer. So it's not possible to do an experiment in a star's life cycle. So instead what we do is use a telescope, and we observe thousands and thousands of stars at different points which are all different points in their life cycle, and we piece them together, and from there we're able to figure out what the life cycle of a star is. In terms of biology, finding out what birds evolved from is an example of something that's by observation, because this is something that is historical. It's something that's happened in the past. It's not something that can really be replicated in an experiment. So what do we find out about where did birds evolve from? Like I said, experiments cannot be used for anything of historical nature. So what we do is we observe fossils. And fossils are the preserved record of life in the past. Inside of this rock, I have a fossil. And all I have to do is just open this up a bit. And here you see the fossil of a fern leaf. And you see the darkened part on that? That is really the carbonized remains of all that's left of the fern leaf, which lived millions of years ago. What happened was the fern leaf fell on some sand, probably on the shore of a lake or near a river, and it got buried, like a flood came over it, or maybe it was tides or something like that, and it didn't decay because there's no oxygen and so it remained long enough for there to be an impression of it when the sand turned into sandstone. Now, Darwin's theory of evolution, it predicts that species today evolved from species of the past. And so that birds had to evolve from an earlier group of animals. And one way that we can test this is to see if there are fossils where there's something that is shows a transition between birds and what they evolved from. It should have some characteristics of birds and some characteristics of whatever it came from. And in the 19th century, they found one. This is the most famous of the transitional species, Archaeopteryx. And the Archaeopteryx lived in the Jurassic, which was in the time of the dinosaurs. And it has characteristics of both reptiles and of birds. What we have over here is a picture of that's taken from fossils of Archaeopteryx. And over here we show that it has the wing of a bird. It was able to fly. But it also has characteristics of reptiles. Like, look at the tail here. This tail here, if you take away the feathers, it basically is a reptilian tail. Birds today, they have very, very short tails. And just think of a chicken. You can see the little tailbone that's there. It's very tiny. But usually when we see a long tail in a bird, it's not an actual tail with bones and skin. It's basically feathers. Another reptilian feature is that it had a toothed beak. Birds today don't. And it had claws on its front limbs. Today there's only one species of bird which just has one claw instead of two, and only has that as a juvenile. So from this, scientists concluded that birds evolved from reptiles. Other fossils that we've discovered since the 90s have shown that birds actually evolved, the group of reptiles that they evolved from, which are dinosaurs. In particular, the raptors is what they evolved from. Now here are the steps of the scientific method. Step one is to do research, so that you don't have to completely remake the wheel. Find out what other people have learned. Do research in the library. You can network with other scientists at conventions, over the telephone, by Twitter, or you can also just observe nature. And that will lead you to formulate a question saying, that's strange. And when you formulate the question, that will lead you to making a prediction or a hypothesis. When you've got the hypothesis, then you test that hypothesis to see if your prediction is valid or if it's not. And once you've done your experiment, you have data, you analyze the data. And that leads you to draw a conclusion. Does your experiment, does the data from your experiment, does it validate or does it agree with your hypothesis? Or does it disagree? Does it disprove your hypothesis? And after that, then either the test is redone. Usually if it's redone by another scientist. This is frequently done when the experiment is something that's controversial. Or just go on to or it'll lead you to go on to the next level. You've learned a bit about the universe, and it'll lead you to find out more about the universe. It will lead you to more questions, which lead to more hypotheses, and so on. Now, why do we have to do experiments? Up until the Renaissance, nobody did experiments. They just used logic. They used philosophy. But the thing is this, what's logical is not necessarily true. If you take physics in college, you'll find that when you get into the things that are very, very small, like at the atomic scale, things happen there which are just bizarre. And when you look at other things, like some other things at a larger scale, we'll see one in just a little bit, that you're going to do a little experiment at home. Something that's logical isn't true, and probably Zeno's paradox is one of the most famous ones, and I'm going to show you a video that I took off of YouTube.
The tortoise challenged Achilles to a race, claiming that he would win as long as Achilles gave him a small head start. Achilles laughed at this, for of course he was a mighty warrior and swift of foot, whereas the tortoise was heavy and slow. "How big a head start do you need?" he asked the tortoise with a smile. 10 meters, the latter replied. Achilles laughed louder than ever. "You will surely lose, my friend, in that case," he told the tortoise. "But let us race, if you wish it." "On the contrary," said the tortoise, "I will win, and I can prove it to you by a simple argument." "Go on then," Achilles replied, with less confidence than he felt before. He knew he was the superior athlete, but he also knew the tortoise had the superior wits, and he had lost many a bewildering argument with him before this. "Suppose," began the tortoise, "that you give me a 10-meter head start. Would you say that you could cover that 10 meters between us very quickly?" "Very quickly," Achilles affirmed. "And in that time how far should I have gone, do you think?" "Perhaps a metre, no more," said Achilles, after a moment's thought. "Very well," replied the tortoise. "So now there is a metre between us, and you would catch up that distance very quickly?" "Very quickly indeed." "And yet in this time I shall have gone a little way further, so that now you must catch that distance up, yes?" "Yes," said Achilles, slowly. "And while you are doing so, I shall have gone a little way further, so that you must then catch up the new distance," the tortoise continued smoothly. Achilles said nothing. "And so you see, in each moment you must be catching up the distance between us, and yet I, at the same time, will be adding a new distance, however small, for you to catch up again." "Indeed it must be so," said Achilles wearily. "And so you will never catch up," the tortoise concluded sympathetically. "You are right, as always," said Achilles.
Now here we're going to find out what a hypothesis is. It's an educated guess that can be tested. If it cannot be tested, then it's not a hypothesis. Like, for example, a statement that 50 angels can fit on the head of a pin can be an educated guess. You can base it on quite a bit of logical reasoning, but it's not something that can be tested because we have no way of detecting angels. It is also a prediction. It is not a question. If on an exam you asked what the hypothesis is and you wrote down a question, it will be marked wrong. So if you wrote down which falls faster, a person or a pen, that's wrong. If you instead made it a prediction, a person falls faster than a pen, that would be correct. And the experiment tests the hypothesis. Together, we're going to test a hypothesis. The hypothesis is that heavier things fall faster than lighter things. And I'd like all of you to do what I'm doing right now, which is I'm standing on my chair and put an object, in my case I have a microphone, and for you put something like a pen in your hand, not something like a paper, because air resistance will sort of mess up the experiment. So what we're going to do is we're going to test this. Now, if the hypothesis is correct, my hand should fall faster than the microphone. So this goes faster, this goes slower. So you should observe something like that, where the hand and the microphone are no longer in contact. Now we're going to walk off the chair. We're not going to jump off. Two reasons for that. One reason is head may hit the ceiling. The other reason is when you go up, it's going to end up sort of like throwing or pushing your pen up, so that's going to mess up the experiment. So everyone, let's walk off and see what happens. As you saw, the microphone, let's down a bit, the microphone never left my hand. So the hypothesis has actually been disproven. What actually happens is that all objects fall at the same rate. Heavier objects do not fall faster than lighter objects. And Sir Isaac Newton and also Galileo were the people who first tested this. For thousands of years, people believed that heavier objects fall faster than lighter objects until Galileo and Newton showed that they fall at the same rate. Now, a theory is a hypothesis, but it's a hypothesis that has passed these tests and been validated, not proven by experiments. Disproving a hypothesis is relatively easy. You just did it. It's very easily you disprove the hypothesis that heavier things fall faster than lighter things. Proving it is impossible because it may be false in conditions you haven't tested. Like Newton's theories of gravity was basically seen as so true that they called them laws, that they describe what really was going on in nature. And then about 100 years ago, in the early part of the 20th century, Einstein came up with his theory of relativity, which predicted some different things. So scientists did experiments, they did observations, and they found out that in certain conditions where Newton's theory predicted one thing and Einstein's theory predicted another, Einstein's theory was the one that was validated. Newton's theory was disproven. So today, while we learn about Newton's theories of gravity, it really describes very accurately the way things happen on Earth under extreme conditions. Newton's theory breaks down, and it's not one of the accepted theories of physics. Einstein's theory of relativity is still accepted, and we have another theory, quantum mechanics, which is accepted too. Now, here are your questions that I'll be collecting tomorrow. Not the questions, but your answers to the questions. If you don't remember or you don't have in your notes the answers to these, just feel free to go back into the vodcast and get the answers. First one is, what is a hypothesis? 2, what is a theory? And 3, what are the steps of the scientific method? So that concludes this vodcast, and I will see you tomorrow.